one has a big acceleration. And by the way, it is in the same direction. So whatever the direction is of the influence, that is the direction of the change. So I guess I should jot that down. The net force and acceleration are always in the same direction. So if your external environment gives an overall force in a given direction, that is the direction in which the acceleration will happen. This one will also accelerate, but as we found, because it has more mass, it'll accelerate far less. So I'll draw that arrow shorter. Now hopefully this is a common everyday thing that you know, right? If you push the same, exert the same amount of effort on a small mass, right? You're not going to get the same reaction as if you go and you push on something very large, right? So that is because of the mass. In fact, I want to characterize M is my measure of inertia. Okay? So something's mass will quantify that concept we were talking about earlier. So we talked about inertia as this idea that objects want to keep doing what they're already doing. But how badly is it that they want to do that? Okay? So inertia measures the stubbornness to changes to the motion, which of course is acceleration. So if something has more mass, it means that it's more wanting to inherently stay doing what it's doing. And if it has more mass, then it will not react as strongly, it will not accelerate as much in response to your force. Whereas things that have low mass don't have as much inertia. They have some, but they don't have as much. So yes, they also are stubborn to changes. They won't make any changes unless you force the issue. But small masses have less stubbornness to changes. And so if you apply a particular net force, you'll get a much larger acceleration. So mass is basically the way we quantify how badly does something want to resist change. Okay? So let me try to give you some idea of what a Newton is. If you want to try to visualize how much 1 Newton of force is, we can think of it as the amount of force required to take 1 kilogram and accelerate it by 1 meter per second per second. Okay? So let's try to visualize this and get a kind of an intuitive idea of how much force a Newton is. So I'm going to hold a 1 kilogram mass in my hand. Okay, maybe like a small rock or something like that. So maybe about 2 pounds. Okay. So about 2 pounds. I can imagine it holding it in my hand there at rest. It is not going to do anything on its own. It wants to stay at rest. If I want to force the issue, I'm going to take it from rest to a speed of 1 meter per second in 1 second. So 1 meter per second, that's not very fast. It's maybe 2 miles an hour. And so over the course of a second, I'm going to take this rock and I'm going to take it from rest to about 2 miles an hour. So 1 Newton is the amount of force that it would require me to do that. That's not very much force, right? So 1 Newton of force is not like a bunch of force. Okay? Does that make sense? Of course, if it were half a kilogram, which is a lot less stubborn, well, we could, with the same effort, cause it to go twice as fast from rest in a second, right? So 0.5 times 2, that still multiplies out to 1. So 1 Newton will do different things to different masses, right? So I was just trying to give you a little bit of a flavor of how to visualize a Newton, okay? So that's Newton's second law. Of course, if you want to just do it without the vector hats, and you can just use sizes, you can do that. For instance, if you take the size of your net force and divide it by the mass, you'll get the acceleration, okay? That's really kind of all there is to Newton's second law. In fact, let me double check if I didn't miss anything. Yeah, that's pretty much it. So, it may surprise you to learn that that equation is really kind of all we're going to do for homeworks 4 and 5. Now you look at that, it's 3 variables, doesn't seem very complicated, but there's a lot that can go into this. So let me give you a little bit of an outline where we're going. I guess let me go over here. Newton's law, Newton's second law, kind of forms the cornerstone of, in some ways, the entire class. It is the thing that allows us to connect the environmental influences that act on something with how that object reacts. Okay, so it allows us on the left-hand side to say what's the overall environmental influence on this object, and on the far right, what is its acceleration? And of course, the third ingredient is the inherent stubbornness that the object has to change, the mass. So what do we do with this? Well, if the acceleration is constant, okay, so if we discover that we have a constant net force acting on a usually constant mass, so a constant net force and acceleration, well, we have a whole toolkit which we can analyze the subsequent motion, the constant acceleration equation. The only difference is that in your previous work, those accelerations usually came on a silver platter, right? Either they were handed to you in the problem, or I handed you once, so I never had to give it to you again, what is the acceleration of gravity near the surface of the Earth? I guess there were a couple problems where I gave you everything else and you had to figure out what's the acceleration. But the point is that you were never capable of looking at a situation and computing the acceleration yourself. Okay? So now we have a way to do that. If someone gives you the net force, you can find the acceleration. Okay? Let me give you a little bit of a preview. What happens if you don't have constant acceleration? You have a non-constant net force and a non-constant acceleration. So you have some kind of evolving influence over time. And I mentioned that we really don't do that at the moment, right? All your really serious problems on the homework so far have been constant acceleration problems. I think there were a couple problems on homework 1 with these crazy bugs flying around every which way. And obviously it was really limited what I could ask you about those situations. You certainly couldn't tell me about every single moment in those things. The way we'll handle these is actually with something called the energy method. And we won't get to that for quite a while. I think it's homework 7 or 8 maybe. We won't get to it for a while. First we have to do forces. So that will be the subject of homeworks 4 and 5, and that's the cutoff for exam 1, but then also homework 6. Okay? So first we get comfortable with forces and what I call the force method. Then we start to figure out how to talk about energy. Now, what are we going to spend homeworks 4, 5, 6 on? It seems like a pretty simple law. Well, here's what we have. If someone gives you the net force that acts on something, that's given you a gift, okay? They've somehow encapsulated 2 or 3 or 17 different environmental forces and somehow figured out, here's your executive summary, this is the overall force. So one thing we have to do is we have to learn how to combine individual forces into the net force. So what do we do if we get given a bunch of forces all pointing in all different directions and different amounts of newtons? How do we combine them properly? And the last thing is that if you're going to combine individual forces into a net force, you have to know what they are. So we're going to be learning about various forces that are commonly occurring, so that we might include them on our list of individual forces that are relevant for a problem. So identifying individual forces. So let me just give you a little bit of a preview where we're going with this. First, we'll talk about the force of gravity. We'll talk about the force from a rope or a string called tension. We'll talk about that support force from a solid surface called the normal force. And these will all be on your homework number 4. Then we'll introduce the force of friction. That, along with some advanced applications, is your homework 5. These will all be on exam 1. But then we'll continue on with forces even in homework number 6. And I don't want to give away all the surprises, but it's basically more of the same thing, learning about forces and how they work in the real world. Okay? So you can see that this forms all kind of an interconnected thread of logic. And you're not necessarily always going to go from left to right. Okay? I should really draw double-headed arrows here, because of course this is all one interconnected thread of logic. You can come in at any point and go right. You can come in on the right, end up to the left. You can come in on the left, go to the right. You can come in somewhere in the middle and go either way, right? It all ends up being an equation that you solve, and you can leave out anything in the equation and solve for it, right? So just because it can be intimidating, how does this all work? Where do I start? Where do I begin? I will give you what's called a forces problem-solving strategy. It's basically what you see on the board, but put into a much more nuts and boltsy thing like step 1, do this. Step 2, do this. And it's a recipe that'll always get you through. Okay. Again, this is your homeworks 1 through 3. I think there might be one very simple question on homework 3 at the end about this law, but mostly homeworks 4, 5, and even really homework 6 are kind of on this stuff. And then when we get to homework 7, I must be homework 7, we'll look at this. Okay. So this is kind of like a master plan for what we'll be up to in the upcoming weeks. And I wanted to kind of have it there just so you kind of know where we're going. Now before I kind of get with that program, there's one remaining order of business, which is to talk about Newton's third law. So before I do that, are there any questions? Okay, so let's talk about the third law. And let me put it in this way so that you can see why they're numbered the way they are. So if the first law is an object that's left alone, right? That's the natural state of an object that we have to establish first. It's nice to have it as its own law, even though mathematically it is contained in the second law. The second law says when an object is affected by its environment. The third law is how the environment is then affected by the object. So you can see it flows very naturally. if kind of thought about in this way. If the second law talks about how an object is affected by its outside environment, the third law says, well, how is that environment affected back by the object? Okay? And in fact, we're going to find that the distinction between object and environment is completely just for practical purposes only. When we say object, it means the object we care about. So how is it affected? When we say environment, there's no particular distinction between object and environment. What is an environment? Environment is objects or objects we don't care about, except as a cause or influence, I guess, influence on the object of interest. Okay? So this is just a way of kind of cleaving the entire world, which is made out of a bunch of different objects, into objects that we care about and objects we don't. The object we care about, we call that the object. That's the mass in Newton's second law. And then everything else, even though those are other objects, we just care about those as how do they affect our one object of interest. We don't necessarily care how that affects back the environment. Okay? So the world is just full of objects, and your decision in a problem is how you're going to cleave off the situation into an object and then everything else being the environment. So let's talk about that. So let's say I have two objects, A and B. So here's what Newton's third law says. If object A exerts a force on object B, comma. Okay, so before I fill in the rest of the clause, let me point out, it is not the job of the third law to say whether or not A exerts a force on B. The job of this law is to say, if this is true, then there will be something that follows from this statement. So you need some other means to figure out, is this true? But then the third law will say, then something must follow. Then what must follow is that object B exerts a force on object A. So you cannot exert a force on something else without that something else exerting a force back on you. And furthermore, Newton's third law tells us that the force, the second force, is equal in size and opposite in direction. So it puts very, very strict constraints on what is the other force, okay? So let me draw this in, okay? So I'll go back to my situation. I somehow know that A exerts a force on B. So let me draw a force vector here. I somehow know that B, let's say I somehow know that B is pulled toward A. Okay, it doesn't have to be that way, but if I somehow know that. By the way we notate this is FBA. Okay? The notation is that the first is what is on, so that force acts on object B, and the second subscript is where it comes from, so it comes from A. Some people like to put a comma in between. I think it's just wasted writing. If I call them instead objects 1 and 2, this would be F21 instead of BA. Reason why people like to put a comma in between, because otherwise it looks like F21. Okay? I'm never going to give you double-digit numbers of objects, so You shouldn't have to worry about if it's 21. It's 2 and 1. They are single digits, okay? So that is the force that B feels from A. And if I somehow know from other laws or other considerations that that is true, then Newton's third law tells me that there will be a force that B exerts on A. So I write this as the force that A feels from B. So what it's on is on A, so I draw it attached to A. Where it originates from is B, so that's the second thing. And these two forces are equal and opposite. So one of the ways that you can write the third law in kind of a shorthand notation is this. Those two forces are exactly equal, except for one is in the opposite direction, and so hence I need an extra minus sign to equate them. I can't just say they're equal and opposite. Okay? So let me go ahead and show you this. I'll be object A, and I'll pick this chair to be object B. So let's suppose that I decide to exert a force on B, so it pulls toward me. If I pull the chair toward me, I'll get pulled toward the chair. So we see that the force is together, right? So it's an attractive force. I pull the chair pulls me. I cannot pull the chair without the chair pulling me, okay? It need not necessarily be attractive. I'll show you the opposite example. If by external considerations, I somehow know that the force on B from A points this way, maybe it points that way, but Newton's third law severely constrains that the force back on A is equal and opposite, okay? So if I push B away, I will get pushed away myself. I can show you that example as well, because of course, I can manipulate this chair however I want. So I can push the chair away, but it will push me away. So I can't push it away without feeling a force back on myself. So there's really only two options here. There's attractive and repulsive. That's it. Now, one of the things that is a common misconception is that these forces can't be equal and opposite. Now, if I push the chair away, you notice the chair moves a lot more than me. That is not because the forces are different. What is the difference between me and the chair?
Mass.
The masses, which means that even if you apply the same amount of force, if I have way more inertia, I'm not going to accelerate as much in response, okay? So the forces are equal and opposite, but if we're talking about me being a large mass, I will accelerate relatively little for that amount of force, whereas the chair has a relatively small mass, and it'll accelerate quite a bit. Make sure you understand that Newton's third law does not dictate that the motion you see, the change to the motion or acceleration, is the same. The only thing it dictates is that the forces are equal and opposite. The accelerations are by no means necessary for that to happen, okay? So the forces are equal and opposite. The accelerations generally do not have to be, okay? Okay, so I guess before I do anything else, let me talk to you a little bit about what these things are called. These forces always appear in pairs, okay? You'll always have both of them. They're called action-reaction pairs. Forces always appear in pairs. Now, which one is the action and which one's the reaction? It doesn't really matter because they both are always there. You either have both of them or neither. You can never have one and then the other one comes along later. They both appear always together. You may have heard the shorthand form of Newton's third law. For every action, there is a reaction. Or maybe for every action there is an equal and opposite reaction. That is a dangerous statement because it makes you think you understand what's going on, but there's a lot that is kind of missing or vague in that statement. First of all, what is an action? It's a force. What is a reaction? It's another force. Which one is which? It doesn't matter. It also doesn't make it clear what these things are acting on. So for instance, if you're sitting on the couch vegging out and your friend says, hey, get up, let's go do something. And you say, I'm sorry, but Newton's third law does not allow me to do that, because if I try to take the action of leaving the couch, there'll be an equal and opposite reaction that keeps me on the couch. That's of course ridiculous. You're perfectly capable of getting up. It's an abuse of Newton's third law, okay? The thing that I want to point out is that both of these forces are acting on different things. One force is acting on one object, one force is acting on the other object. So these are perfectly capable of both accelerating. They'll either accelerate